Hello. The next problem is kind of similar to the previous one, but is more difficult in two ways. The first one is for the guessing part, and the second one is for the part of the proof of the guessed hypothesis. Let's start. Sequences, guess and proof, problem 3 with two base cases. And here is its formulation. We are supposed to find the closed formula for the sequence AN if we have two first elements, A1 equal to 3 and A2 equal to 7. And then for n greater than or equal to 3, we have this formula for AN. You see that AN depends on both the previous element in the sequence and the one before that. So A3 would depend on both A2 and A1. So you see that we need two starting points, and this is why we will also need two base cases in our proof by induction. Okay, so now you know how this sequence is defined, and first we will have to try to guess the closed formula for this sequence, starting from this recursive formula, and then we will have to prove this closed formula. Okay, so let's start. We have A1 and A2, and now we will start with n equal to 3, because the first element which we don't have is A3. So from this formula, for n equal to 3, we see that A3 is equal to 3A2 minus 2A1, right? Just plug in n equal to 3, then you will get A2 here and A1 here. And now we can apply the definition of because of the sequence, because we have the two first elements, both A1 and A2. First we have in our expression for A3, first we have 3A2, which means 3 times 7, it is 21, minus twice A1, which is 6. So altogether we have 21 minus 6, it is 15. Okay. Then we can try n equal to 4, and again now we apply the same definition, but this time with n equal to 4. So we will get A4 is equal to 3 times A3 minus twice A2. So again A4 depends on A3 and A2. And here A3 we got this result 15 in the previous step. So here we have 3 times 15 is 45, and then we have to subtract twice A2. A2 is 7, so it will be minus 14. And then we get the result 45 minus 14 is 31. Okay, let's try one more before we can try to make some guess. N equal to 5, again the same formula, this time for n equal to 5. It gives us A5 is equal to 3A4 minus 2A3 is equal to. A4 was computed in the previous step, it was 31, 3 times 31 is 93, and we have to subtract twice A3. A3 was 15, so we have to subtract 30. And the result is how much? 63. Okay, now it's time to make some guess. Let's have a look here. We get the numbers 3, 7, 15, 31, and 63, sorry. I was already thinking 64, because all these numbers look like the powers of 2 minus 1, right? So let's start writing down. Here for the first one, we will have, this is 4 minus 1, so it is 2 squared minus 1, right? The next one is 2 to the third minus 1. Then 15 is equal to 2 to the fourth minus 1. 31 is 2 to the 5th minus 1, so it looks like we have got our closed formula, right? And the next one is 2 to the 6th minus 1. So altogether we can make a guess, which seems kind of plausible, that our Tn will be that an is equal to, look, a1 was 2 squared minus 1, a2 was 2 to the 3rd minus 1. So you take always 2 to the power which is 1 larger than the number of your element. So it will be n plus 1 because it is 1 larger than n, and then we have to subtract 1. So we got our hypothesis that the closed formula for our sequence an is equal to 2 to the power n plus 1 minus 1. And now we have to prove this by induction, and for this particular problem, I have decided to not to keep my color coding. So you see that there is no orange color, because I will prove that an is that T of n is true, provided that the two previous, that the statement for two previous numbers are true. So that T of n minus 1 and T of n minus 2 are true. Why? Well, because then I can simply literally apply this formula for an in order to use the induction assumption for n minus 1 and for n minus 2. But this is why I also dropped this regular color, so that you don't get a wrong impression that it's maybe something else going on. So in any case, we have to start by two base cases, because in order to start with our computations for some number, we need the values of the elements of the sequence numbered by two numbers before. So we have to prove T of 1 and T of 2. And what is T of 1? T of 1 tells you that a1 is equal to 2 to 1 plus 1 minus 1. Is it true? Look, we have here the definition of a1. a1 is equal to 3. And let's see if it agrees with the hypothesis T1. So 2 to 1 plus 1 is 2 squared, it is 4. 4 minus 1 is 3. So we get exactly what we were supposed to get. So T of 1 is true. What about T of 2? According to this green formula, T of 2 is that a2 must be equal to 2 to the power 2 plus 1 minus 1. And it is 2 to the 3rd is 8 minus 1 is 7. And 7 is exactly what a2 is by definition. So we have proven that the base case is true for this T of n. And now I will write down for some n greater than or equal to 3, because now we have to show that Tn for some n greater than or equal to 3 is true, provided that the two previous ones are true. So what is T of n minus 1? Well, you see it here, right? You have defined T of n, and T of n minus 1, it is the expression for a n minus 1, right? So we simply plug in n minus 1 instead of n in the definition for T of n. And this green formula tells me that n minus 1 should be equal to 2 to the power of n minus 1. And the same with T of n minus 2. We use the same green formula here, but now we have to plug in n minus 2 instead of n. So n minus 2 is equal to 2 to the power of n minus 2 plus 1, it is n minus 1, and minus 1. So now, this will be our induction assumption. So we assume that these two are true for some n which is greater than or equal to 3. And we know that we have some starting points, right? For which the hypothesis is true. So this is our induction assumption. That these two are true. And now we have to show that with these assumptions, T of n is true. And T of n is this formula in green, which you have above in my iPad. So now, assume that for some n which is greater than or equal to 3, both, and now I will use the same colors, both, no, it is a wrong color, both T of n minus 1 and T of n minus 2 are true. Show that this implies that also T of n is true. And now for once our T of n, it is this formula which is in green. So usually there was another color coding, but I explained that in this particular case I simply want to use this formula literally without changing n into n plus 1. So this is why I kept this formula in green. Okay, so our purpose is to prove that this green formula holds for this n for which we know that T of n minus 1 and T of n minus 2 are both true. So now I have to show that an is expressed exactly as in this green formula here above. Okay, so an is, by definition of our sequence here, by definition, equal to 3 times, and now I will write n minus 1 in gray so that you know what I have to put instead of this element. And then we continue with minus 2 times n minus 2. So now you see that I have expressed my an with help of this an minus 1 and an minus 2, for which I have assumed that the induction hypothesis is true. And this means that I get here 3 times. And now the expression for an minus 1 is 2 to the power n minus 1. So here I use the induction assumption. The induction assumption. And then I continue with my formula. Further I have minus 2 n minus 2. And here I can also use the induction assumption. Here I will get 2 to the power n minus 1 minus 1. And now you see we are almost done, you will see. Now we have to perform this multiplication, and this will give us 3 times 2 to n minus 3. This is the first expression. And the second one will be minus 2 times 2 to n minus 1, it is 2 to n, and then minus 2 times minus 1 is plus 2. And now you see we are almost done, because if we group together these two here, then we will get here, you see that these two terms which I have marked in green have a common factor, which is 2 to the power n, and in the parentheses we will have 3 from the first term and minus 1 from the second one. And then these two other terms in this expression put together give us 2 minus 3, it is minus 1. So then we get here 3 minus 1 is of course 2, so this first green expression gives us 2 to the power of n times 2, which is 2 to n plus 1, right? And then we still have minus 1, and you see this is exactly what we were supposed to get. This is our t of n, you see? So I can take the same green color and mark this an in this green color. So assuming that t of n minus 1 and t of n minus 2 are both true, we get that, t of n is also true. So we are done. So now this last magical statement, according to the principle of mathematical induction, PMI, the statement is true for all n in natural positive numbers, because, well, we start with A1, right? So here you see this problem was harder. To begin with, it was harder to make a guess, and then we had a special type of induction with 2 base cases, because, well, we needed results for 2 numbers before in order to formulate the result for the current number. But it went well, and we are done with this one. Thank you for watching. Bye bye.